Now we'll discuss about universal relay, RX diagram and torque equation. So universal relay, it's an electrically operated switch. So many relays use an electromagnet to mechanically operate a switch. Other operating principles are also used, such as solid state relays. So the first relays were used in long distance telegraph circuits as amplifiers. Relays were used extensively in telephone exchanges and early computers to perform logical operations. And the solid state relays control power circuits with no moving parts, instead using a semiconductor device to perform switching. So relays with calibrated operating characteristics and sometimes multiple operating coils are used to protect electrical circuits from overload or faults. So these are performed by digital instruments called protective relays. Magnetic latching relay requires one pulse of coil power to move their contacts in one direction and another is redirected pulse to move them back. And magnetic latching relays can have either single or dual coils. So on a dual coil device, when polarized voltage is applied to the reset coil, the contacts will get transition. And AC controlled magnetic latch relays have single coils that employ steering diodes to differentiate between operate and reset commands. The universal torque equation governs the application of all type of relays. There is changing the signs of some of the terms, ignoring them entirely, that is T equal to K1 I square plus K2 V square plus K3 VI cos theta minus tau plus K. So K2, K3 can be considered as 0, while K will be negative as it is used to describe restraining torque. The equation will then become T equal to Ki square minus K. In case of directional power relay, K1 and K2 can be considered to be 0 while K can be considered to be negative. Next is the electromagnetic relay. These relays operate by electromagnetic action. So the main principle is the flow of current through an electrical conductor causes a magnetic field at right angles to the current flow direction. So the magnetic field produced by passing current through coil can be used for various purposes such as inductors, construction of transformer using two inductor coils with an iron core, and this is similar to permanent magnets used to attract magnetic objects, but here the magnetic field can be turned on or off by regulating current flow through the coil. So thus we can say that electromechanical relay operation is dependent on the current flowing through the coil. Next is the RX diagram. The useful way of representing the operating characteristics of the relay is an RX diagram that is shown here. So Z is equal to K equal to radius of the circle. When Z, that is the impedance of the line up to fault location measured from the relay location, is less than K, the relay will operate. That is, the fault location lies inside the circle. So if it is outside the circle, the relay will not sense it, and hence the zone is the blocking zone. The operations of the relay depends upon the magnitude of Z and not on the angle phi, as Z is the radius of the circle having equal magnitude along the circumference of the circle from the center. So the figure indicates that the operating time of this relay is constant irrespective of the distance within the protective zone. Torque equation. So the universal torque equation explains the working of the electrical relay, that is the torque produced by the interaction of the flux of same winding or between the fluxes of both the windings, that is torque developed by the current windings is K1 I square, torque developed by voltage winding is K1 V square. If both current and voltage windings are used, the torque developed by the interaction between the fluxes is given by the equation K3 VI cos theta minus tau. So theta is the angle between V and I, and tau is the relay maximum torque angle. So here if the relay has current, voltage and torque angle, the torque will be developed. It will be given as T equal to K1 I square plus K2 V square plus K3 VI cos theta minus tau plus K4. K1, K2, K3 are the tap setting or constant of V and I, and K4 is the mechanical restraint due to spring. So for example, in an overcurrent relay, K2 equal to K3 equal to 0, Because of the absence of voltage windings, the torque equation becomes T equal to K1 I square minus K4. So the negative sign attributes to K4 because the spring produces restraining torque. So the developed torque will be given as T equal to K3 Vi cos theta minus tau minus K4.